Title of my talk is Entanglement, Entropy, and Gauge Theories. Now, I should apologize to some of you who have heard me speak about this on earlier occasions. I've been working on this topic for a few years, and somehow it's taken me that much time to really feel like I understand it. There's still a few issues which I had hoped to sort out by the time I came to give this talk, but which still remain, and I'll tell you about some of them as I go along. So I thought, let me at least try to give this talk one more time. The other reason is that, in fact, my thinking on this subject has been influenced to a very good extent by the work of Horacio and Mariana and others in the audience who I'll get a chance to refer to as I go along. So I couldn't resist the temptation of speaking about it here. Okay, so what I'll do is I'll start with an introduction and tell you why there is something of an issue when it comes to thinking about entanglement, entropy, and gauge theories, what the issue is, and so on. Then I'll give a definition, which I'll call the extended Hilbert space definition, discuss some of its properties, how it applies more or less immediately to all kinds of gauge theories, and also try to understand that definition more from an operational point of view, namely in quantum information theory. They have an operational way of trying to define the entanglement of a bipartite system, say, through quantum distillation or dilution. And I'll tell you what part of this result you get from this definition corresponds to the extractable part. This discussion will be on the lattice, just to keep everything well defined. And after that, we'll go to the continuum limit, where things become more universal. And in particular, as a test case, I'll discuss the free U1 theory, Maxwell theory in 3+1 dimensions in the continuum limit. This is just about the simplest gauge theory one can think about. And there were some puzzles in this theory itself in the literature. And I'll tell you how some of this understanding can help understand those puzzles. And then we'll go further in the continuum limit to discuss more ultraviolet safe quantities like the mutual information or relative entropy, and see how they become really quite universal, independent of much of the ambiguity that might come with a particular definition for these, that in the continuum limit, these quantities become independent of that kind of ambiguity. So it's a kind of fairly satisfactory picture, I think, that we are now coming to when it comes to entanglement in gauge theories. And finally, I'll end with conclusions. Okay, so why is the entanglement entropy in gauge theory somewhat non-trivial to define? I'll come to that, but first let me just say, I don't have to say this to you all, it's clearly an interesting question. Entanglement is important, gauge theories are ubiquitous in nature, so this is well worth thinking about. Physically, this is a non-trivial issue because the excitations in a gauge theory, unlike, say, a spin system, are inherently non-local. For example, in the form of Wilson and 't Hooft loops. And so if you have a system with these non-local excitations, and you're trying to understand how entangled is some local spatial region with the rest, that's a somewhat non-trivial issue. Okay, so that's the physical reason. As we go along, I'll try to make that more precise. Now, but let's start first with a system, just to orient ourselves, which has manifestly local degrees of freedom, like a spin system. Here, the entanglement entropy, as you all know, is straightforward. Let's say we take a two-dimensional lattice and a spin system, which consists of a qubit, a spin half degree of freedom at each site of the lattice. Okay, so a two-dimensional Hilbert space at each site. And suppose we were interested in the entanglement of some sites with the rest, then it's very straightforward. We'll call the region of interest the inside and the rest the outside. They don't have to be geographically contiguous, but that's just a convenient notation. Now, the full Hilbert space in this problem is obviously the tensor product of the single site one qubit Hilbert spaces, Hi. And this admits a tensor product decomposition in terms of the Hilbert space for the qubits in the inside lattice points and the outside, H in tensor product H out. And this fact that the Hilbert space can be split like this is what makes things very straightforward, because once that's the case, you take your favorite state whose entanglement you want to compute, trace out the outside degrees of freedom to get a density matrix, and compute its von Neumann entropy, trace rho log rho now in the inside Hilbert space, and that gives you the entanglement entropy. Okay, so the crucial point here is that the Hilbert space admits this tensor product decomposition between the region of interest and the rest, the inside and the outside. Now let's come to a gauge theory. I think I already said this. There's no, and as you'll see, what happens is that the physical Hilbert space of states in this case does not admit a tensor product non-trivial, does not admit a tensor product decomposition between an inside and an outside Hilbert space, at least not automatically. To understand that, let me work with the lattice gauge theory, and I'll work in the Hamiltonian framework, so time is continuous but space is on the lattice, and the discussion will be quite general. So here is a two-dimensional spatial lattice. Now the degrees of freedom of the gauge theory live on links. You can have matter as well that lives on the vertices, but for now let's just think of a pure gauge theory. So we have linked degrees of freedom, and we might be interested in how entangled are some set of links vis-a-vis the rest. Okay, the linked degrees of freedom could be, say, Z2, a qubit, single qubit degree, if we have a Z2 gauge theory, or a phase degree of freedom if we have a U1, or some non-trivial matrices if we have non-abelian gauge theories. But that's the general structure of gauge theories. Also, I'll work in the Hamiltonian framework. It's convenient to work in A0 equal to 0 gauge, so there are no link variables associated with the time direction. Okay. Now, even though we do go to A0 equal to 0 gauge, as you all know, we still have to impose the Gauss Law Constraint. And what this constraint tells us is that, say we are doing the pure gauge theory with no matter, what it basically says is that the total flux coming into any vertex must be 0. So the total flux coming in, let's say I take a boundary vertex in particular, which is on the boundary of the region of interest with the rest. You have some flux coming in from the outside, some flux coming in from the inside, and they must all cancel, just from flux conservation. Now what that means is that the degrees of freedom on the links outside and inside are not independent of each other, because they must cancel at each boundary vertex. And this lack of independence is what results in the Hilbert space of physical states not having a tensor product decomposition. Okay, so the inside and outside are not independent, and this is the central feature then, and it's true, of course, in any kind of gauge theory, whether discrete or continuous, etc. And in fact, this Gauss Law constraint then couples the degrees of freedom outside and inside at each boundary vertex. Okay, so if you are interested in the solid links, then you have a number of boundary vertices, and you have such a constraint at each of those vertices. It's a local constraint. And this is the essential obstacle or complication, as you'll see, in trying to define the entanglement entropy for gauge theories. Now you might say I can try to deal with it by gauge fixing, but what happens then is that the answer you get depends on how you gauge fix, because physically you can move degrees of freedom on one side or another of the boundary, and so the answers you get are not gauge invariant. And so that's not very satisfactory. Now, as I was saying, a very key paper in this subject was written by Cassini, Huerta, and Rosabel. Actually, I've never met Rosabel. Maybe he's there in the audience. Okay, all right. And they, in fact, proposed a definition in the abelian case. And what they showed there was that there is, if you think in terms of the algebra of gauge invariant operators, say that act on the inside or the outside region, then that algebra has a non-trivial center. And the existence of that non-trivial center is actually tied to the Gauss Law constraint I was talking about, for example. And this presence of a center is how then the Gauss Law constraint shows up as an essential issue in trying to define the entanglement. And what they showed was that by choosing a suitable choice of the center, you can then provide a definition. Depending on which center you use, you get different definitions. Okay? I won't give you more details, but I'll try to connect to this as we go along. And here are some of the papers which I've written on the subject with two students, Sudeep Ghosh, who's a student now at the International Center for Theoretical Sciences, which is a new center of the Tata Institute in Bangalore, and Ronak Soni, who's my student who's just finishing up. Okay, there are several other papers by Cassini and Huerta and collaborators. Nice paper by Radicevic, and actually there's two papers. Paper by Aoki, earlier work by Budovic and Polikarpov. Very nice work by Will Donnelly, who's also here, and also Donnelly and Wall, and there are also more recent papers, which I'm sorry I've not referenced here. Other work by Pretko and Senthil, Ecolin, Verstrate, and collaborators. So there's been quite a lot of work by a number of people, only some of whom I've listed here. Okay, so what's the definition I'd like to propose? The idea is really quite simple-minded, and it is the following. To in fact work in an extended Hilbert space, and which admits a tensor product decomposition between the inside and the outside. Okay, so let me explain what I mean. Let's go back again to this diagram. Let's say we're doing a Z2 gauge theory. So you have one qubit on every link. Now you see immediately that of course there is a underlying or extended Hilbert space obtained simply by taking the tensor product of the Hilbert spaces on each link. All right, that is available in the problem. A general state in this Hilbert space won't satisfy the Gauss Law Constraint. That's why this is an extended Hilbert space, but it's available to us. And the idea is simply to embed physical states in this more extended Hilbert space. Once we do that, the extended Hilbert space, of course, has a tensor product decomposition between the Hilbert space of the inside links and the outside links. And we can then, working in this extended Hilbert space, compute the density matrix for the inside region and the von Neumann entropy from it, very much like we did for the spin system. Okay, so that's the basic idea. We work in the extended Hilbert space, and we try to define and then we define the entanglement entropy because it admits this tensor product decomposition. Now I still have to tell you, to make it totally unambiguous, how I embed a physical state in this bigger Hilbert space. And the way to do it, to get a gauge invariant answer, is the following. The full Hilbert space can be split as a direct sum of the gauge invariant subspace and its orthogonal complement, and we embed the physical state so that it lies entirely in the gauge invariant subspace with no component along the orthogonal complement. Okay, so now we have completely defined how to embed any gauge invariant state in this bigger Hilbert space. The process of taking the traces and so on is also totally well defined. So this is a completely unambiguous, well-defined definition. We take rho in like this, and then we compute the von Neumann entropy. And this is then the extended Hilbert space definition of entanglement entropy that I'd like to propose for a gauge theory. You can also see that it's immediately very general. It applies really, and you can define Rene entropies, etc. also similarly. You see immediately that it's really quite general. It doesn't much matter what were these degrees of freedom. They could have been a Z2 qubit. They could have been a phase degree or non-abelian. You can do this. In all cases, also, if there's matter, you can incorporate that also in a very straightforward way. I should speed up a little bit, but that's okay. Now, this definition has some nice properties. It's unambiguous, as I was saying. It's also gauge invariant. We didn't have to choose a gauge. We did have to work in an extended Hilbert space, so you might worry that perhaps some of the lack of gauge invariance will creep in, but you'll see that's not the case. I'll have more to say about it. So this is actually gauge invariant. Also, this bigger extended Hilbert space comes equipped with a positive definite norm, a semi-definite norm, which meets all the good properties of a norm, etc. And so that means you can show quite easily that the definition we provide meets the strong subadditivity property, etc. So that's also a nice feature. So those are some of the nice features. Let me tell you a little bit about gauge invariance. The underlying reason why the definition is gauge invariant is because of the way we embedded physical states in this bigger Hilbert space, namely that it only lies in the gauge invariant subspace with no component along the orthogonal complement. That means when you actually compute traces and so on, that non-gauge invariant states don't couple. Okay, so that's what happens. But let me tell you a little bit more about it. If the answer is really gauge invariant, we should be able to express it more manifestly in terms of gauge invariant data. So let me try to do that now. And just for simplicity, let me consider a theory without any matter, so just the pure gauge degrees of freedom. Now, just to go back to the essential complication I mentioned before, which was that we need to meet Gauss's law at every boundary vertex. You can also label different sectors of the theory as follows. Let's take the boundary vertices. We can label them in some order, V1, V2, etc. At each vertex, there's some flux, which is net flux, which is coming in from the outside. Okay, so if it's a Z2 gauge theory, there's some Z2 valued flux at each of these vertices. Otherwise, if it's a U1 theory, there's some integer valued flux, etc. And we can label different sectors by the fluxes which come in at each of the boundary vertices. Okay, so that's just a little bit of notation, if you like. So we have these vertices and we have these electric fluxes coming in. And we can think of these as specifying different sectors in the theory. Then the final answer can be expressed, which you get using the extended Hilbert space definition, can be written as follows. It consists of a sum of two terms. Pi here is the probability. So you're starting with a state and you want to compute the entanglement entropy. That state has a probability to be in some flux sector. Okay, I here denotes that sector. That is a particular choice of values for flux at each boundary vertex. So K1 to Kn. And Pi is the probability to be in that sector. So this is like a classical or a Shannon contribution you're getting to the entropy. And then the second term, which I'll call a quantum term, is really the von Neumann. There should have been a trace here, trace rho log rho. The von Neumann entropy in a particular sector. This is the normalized density matrix in that sector, weighted with the probability to be in this sector. So this is the answer, and expressed like this, you can see that it's actually manifestly gauge invariant. Okay, but do keep this in mind because this form of the answer will be important as we go ahead. Now, in fact, this definition in the abelian case matches exactly with what Cassini, Huerta, and Rosabel had defined with a particular choice of center called the electric center prescription. Okay, so it's really the same, just in a little different language that we have come to. Okay, now in the non-abelian case, it turns out there's one extra contribution to the entanglement entropy, and that was also discussed by Donnelly. And this arises for the following reason. As I was saying, the total flux at each boundary vertex has to be 0. Now let's suppose we are doing an SU2 gauge theory, and suppose the total flux carried by the outside link was spin half, was in the spin half representation of SU2. Then the total flux carried by the inside links ending on this vertex must also be equal to spin half, and the two spin halves must fuse to be a net spin 0 state, because Gauss's law says that you can't have any net flux. Okay, and if you take two spin halves and you fuse them to be a spin 0 state, there's an entanglement cost that you have to pay for that, and that arises because in the non-abelian case the representations are not one-dimensional. In the example I gave you, it was two-dimensional. So this extra feature results in an extra contribution to the entanglement entropy. And now, if we think about sectors labeled by the representation of the group under which the flux transforms, and let's say these representations at the vertices V1 to Vn have dimensions D1 to Dn, then the extra, then the full answer can be expressed as a sum of three terms now. These two were the familiar ones. Pi is the probability to be in some sector. This is the weighted average in each sector. And now here's the extra term where you get an extra cost because you have non-trivial irreducible representations which are fusing to give you a trivial representation. Okay, and so at each boundary vertex you get an extra cost. This sum over A is over all the boundary vertices, dAi is the representation in the ith sector at the vertex A, weighted with the probability to be in this sector. So that's the kind of answer, nature of the result you get. And it has these three pieces. Again, as you'll see, this is kind of more like a classical term for reasons, I use this word for reasons that will become clear. This is the quantum piece here. Okay, now, actually these different sectors, the way I'm labeling them with different electric fluxes, in fact are super selection sectors in the following sense. If you are going to do operations involving gauge invariant operators that act either on the inside or on the outside alone, you can't change the electric fluxes. For example, if you're going to act on the inside links alone, you can't obviously change the electric flux coming in from the outside, and you therefore can't change which sector you are in. Okay, so in that sense, if you're going to do local operations, by which I mean physical gauge invariant operations which either act on the inside or the outside, then you're not going to be able to change these sectors, and therefore in that sense they are like super selection sectors in this system. Okay, and what that means is that when we think about operationally trying to extract this entanglement or trying to put it to use for purposes that entanglement can be put to use for, not all of the entanglement I've defined is available to us. Okay, and so let me try to make that a little more precise. In quantum information, as many of you know, there's an operational way to try and define entanglement, and the idea is the following. You have a bipartite system, it has some entanglement, you try to give it a quantitative measure. You provide a quantitative measure for that entanglement by comparing it with a reference system. Let's say some number of Bell pairs, okay? And you do this through a process of either distillation or dilution. And I'll just briefly tell you, just in words, at least a little bit, and then I'll go on. Many of you know this. So let's say the idea in distillation is the following. You start with this bipartite system, and you start with some number of qubits which are initially totally unentangled, and then you allow yourself local operations, unitary operations, which act only on A and some of those qubits, or only on B and some of the others, and you allow yourself also communication, classical communication, and at the end you ask, what's the total maximum number of entangled Bell pairs you can generate from the initial starting unentangled qubits you had? And that maximum number in an asymptotic limit, etc., is then a measure of the initial entanglement in the system. Okay, and in distillation, in dilution, you have a similar, you have an idea where you try to use this entanglement to do teleportation, quantum teleportation, and again, the number of qubits you can teleport becomes a measure of the entanglement. And for usual systems, these two protocols give you the same result, and that then also agrees with the von Neumann entropy, say for a spin system. Here what happens is, since the local operations cannot change the superselection sector, it turns out the full entanglement entropy we have defined is not what you can use for either teleportation or not what you can distill into Bell pairs, only this part of it. The quantum part is what you can distill or use for teleportation. Okay, so if you like, this is the physical part of the entanglement which is actually extractable and usable in the system. And that this is the part which has an operational meaning or definition. Okay, so local operations only act on, okay, I've said all this. So let me go on. I'm already a little behind. And one can give explicit proofs, protocols and so on, showing that that the quantum piece is the maximum extractable piece. This was also done by Verstraete and his collaborators. Okay, now sometimes I just say this because it came up also the other day, and people ask this. They say, suppose you have a gauge theory and it arises in the infrared. What does it mean to say you can only extract this much of the entanglement? And what it really means is this. If you're going to use only gauge invariant operators, this is the maximum amount you can extract. And you might, if the gauge theory is arising in the infrared, then by paying a much bigger cost in energy and exciting the system at higher enough energies, you might be able to extract more. And then this is not the full extractable piece. In some cases, the full extractable piece can be the full answer I wrote down for you. Okay? But if you're just going to use gauge invariant operators, then this is the maximum entanglement you can extract. Okay? So it's a little bit like, all right, never mind. So that's what I mean in a precise way. Okay, now there's another nice property of this extended Hilbert space definition, which is that it agrees with the Euclidean replica replica path integral way of computing the entanglement. As you all know, that's an intrinsically Euclidean way to calculate, so you don't have to talk about states, etc., worry about exactly whether the Hilbert space has a tensor product decomposition, and this actually ends up agreeing with that way of calculating. The essential reason is simply the following. Let's say you're doing this replica trick, again, for a system on a spatial lattice. Basically, you allow each link variable to fluctuate independent of the others. So, you know, the way we think about the replica trick giving us entanglement is, let's say, from -infinity, we do a path integral to generate the state, say at t equal to 0, and then we do that. We also generate, this is, say, the bra, this is the ket or whatever, and then we identify and we compute a density matrix and Rene entropies and so on. And basically, because each link variable fluctuates independently, what happens is the state you generate like this automatically arises as being embedded in the extended Hilbert space. Okay? And you can make this precise. For this reason, the replica trick ends up agreeing with this extended Hilbert space definition. So that's also a nice thing, because the replica trick is a very convenient way to calculate entanglement, and we now understand physically what part of the replica trick answer is extractable, etc. Let me now, in the limited time I have, go to the continuum limit, and you can do that. You start with the lattice, you go to the limit, continuum limit. Since the answer is gauge invariant, you get a gauge invariant path integral with the standard Faddeev-Popov gauge fixing. The only caveat, of course, is that this is to be done, as you all know, say, if you're computing the Rene entropy on a singular n-fold cover, and so you have to regulate it carefully. But with that caveat, you get a gauge invariant path integral, and that's, of course, convenient to try and compute explicit answers. Okay, a little bit about some of the open questions, which I'm going to skip. Let's try to put all the understanding we have gained in use for the simplest theory, as I was mentioning, the U1 theory. Let's be in 3+1 dimensions. Suppose we take a spatial region, which is a sphere with a boundary, which is S2, and we are interested in how entangled is the vacuum state of this theory, how entangled is the inside of the sphere with the rest. Okay, now as you all know, on general grounds, the answer is going to have a cutoff dependent area term, okay, and then there's a term which is a logarithmic piece, log of the, which you could write as log of the radius in units of the cutoff with a coefficient, and that coefficient is a cutoff independent universal quantity, all right. And so let's see what value we get for C. Now, as you all know, many of you know, you can, since this is a conformally invariant theory, it's very easy to do the calculation, and C is in fact related to the A anomaly coefficient. And so what the replica trick path integral or this extended Hilbert space definition gives us is a coefficient minus 31 over 45. I'm mentioning these numbers only because they've been much discussed for this model. So that's what you get. But now you can ask, okay, what part of this result is actually extractable? Because remember, the full answer had this classical piece and a quantum piece, and it's only the quantum piece which was extractable. So we can ask what part of the answer is actually the classical piece, and once we know that, we can get the full, we can obtain from the full answer the quantum piece. Okay, and it turns out that the classical piece is 1/3 log r over epsilon. And this 1/3 is very interesting, is related to basically a free CFT worth of degrees of freedom living on the boundary of this living on the S2 boundary of the sphere. And again, this is this was also discussed in a very nice paper by Donnelly and Wall, and that is very closely related to what you get here. So the result is you can now compute the extractable piece, and that turns out to be minus 16 over 45. And the reason I'm mentioning this is there was something of a puzzle because Cassini and Huerta had done a calculation, I think also perhaps done earlier by Docker, or at least related to that. And they had used a different center, not the electric center. Huh? Oh, I see, it's the other one. Sorry. Stand corrected. Stand corrected. Sorry. Okay. And you know, they'd used a trivial center in which there's no classical piece to the result. And the answer they had got was minus 16 over 45, not the A anomaly result. So this was something of a puzzle. But we now understand it. Both results make sense, but they are somewhat different quantities. One is a sum of the classical and the extractable piece, and the other is the extractable piece. Okay? If you don't have a trivial, if your center is trivial, you only get the extractable piece. So as long as we know what we are calculating, I think one can all agree on what the result is. Okay, so that's the story. I'll just briefly end by talking a little bit about mutual information, etc. in the continuum limit. It turns out that the classical term is actually dominated by very short wavelength modes across the entangling surface, and because they are so short distance, the resulting classical term is dominated by very short distance physics. And what that means is if you have two states and you're trying to compute the relative entropy, then as long as they only differ at long wavelengths, not at the scale of your cutoff, this classical piece will drop out in the difference of their entropies or in the relative entropy. And that means that the relative entropy then only cares about the extractable piece, the one which has an operational significance. Okay? And so that's something nice. Again, different choices of centers mean the classical piece can differ, but again, those differences will go away if you compute these more ultraviolet safe quantities. Similarly, for the mutual information. Okay? Again, that is for disjoint regions will be independent of the short distance, this short distance contribution. So that's sort of nice. And in fact, this argument can be generalized also to non-abelian theories, which are asymptotically free and so on, so that at the scale of the cutoff, they behave basically like free theories. And so you know, in the continuum limit, then things get much more universal, and quantities like mutual information, relative entropy, etc., become independent of these choices of definition, and also correspond to what is the extractable part of the full result. Now, some of this was certainly anticipated, again, in the paper of Cassini, Huerta, and Rosabal, the fact that the classical piece drops out, and also verified numerically for the free U1 theory in 2 + 1 dimensions. And you can make that all a little more precise and see what the dependence on the cutoff is, etc. It's a logarithmic dependence, etc., as I briefly flashed. Okay, I'm out of time. Let me just conclude. So the bottom line is that there is a sensible definition one can give for entanglement entropy in gauge theories. In the continuum limit, things specially simplify, become more universal. And you know, if you don't want to worry about all this in terms of states and Hilbert spaces, then you can just do the replica trick calculation, if you like, for mutual information. Not always easy to do, but in principle, or relative entropy, and then in the continuum limit, that would be a fairly universal result. Finally, of course, it would be nice to try and understand implications for gravity, and that's something we would like to go towards. There's still a little bit of, just to conclude, one thing which we are working on, I'd hope to complete is, since the path integral definition is, of course, gauge invariant, that suggests that you should be able to do the path integral in general in the presence of ghosts, etc. That is true. That suggests that there's even a bigger Hilbert space you might want to work in, which is one which has ghosts, etc., and where physical states correspond to cohomology classes. And this extra freedom can sometimes be useful, and we've unraveled the situation somewhat, but a few things still remain to be understood. So I hope we can complete that. Okay, thank you.
Questions?
Yeah, Igor.
Yeah, there is this phase transition for the entanglement entropy for gauge fields, kind of the confining transition. Has anyone used this new formulation to study it, for example, in Hamiltonian lattice gauge theory?
I see.
I mean, I know it was studied using replica trick by Buividovich, Polikarpov, and others.
Yeah.
There's
been some, I can't say I'm fully up on all the lattice work. There's been some work on the lattice using this, for example, Hamiltonian framework and this extended Hilbert space definition by the Japanese group. But I don't know whether they've studied the phase transition per se. Sorry.
Yeah, it's kind of, the entanglement drops off very quickly as the theory becomes confining.
Yeah. They wouldn't have done it in large N, but I think they might have looked at it.
At small N, it's supposed to quickly drop off.
Okay.
Kind of crossover.
I don't know the answer. I can try to look.
Okay, thank you.
So, if I understand correctly, you said that when you compute the relative entropy on mutual information, the classical piece drops out, right? So, do you think there's some sort of intrinsic physical interpretation for the classical piece? Because it only appears in this.
Well, the classical piece actually carries a lot of interesting information. For example, in the toric code, the full contribution is a classical one, actually, because at low energies, it's a topological theory. There's not much to extract. So, and that gives us a lot of information. So the classical piece certainly has a lot of information in it, but it's just good to know what it tells you. And it doesn't tell you exactly how much you can distill. That's the other part of the result. I don't know, Alexei had his hand.
Instead of extending the Hilbert space, one could also consider meta in the fundamental representation. And then one can map the Hilbert space directly to a tensor product space. Will it give the same result or not?
I've tried to think about it a little bit, but not fully. Well, one would have to be careful not to add extra degrees of freedom due to that matter in some careful way, and then it could perhaps work. It might be basically these different flux sectors one might be able to think of as the outside flux ending in some charge, and in that way set up the problem. But when I try to think about it, I was a little worried that I might be adding in extra degrees of freedom. So as long as you careful enough, perhaps make the extra matter very heavy or something, then that probably should map in some way here. Because instead of keeping track of the outside flux, you could simply say that you have charges on the boundary, which can take various values. But I can't say I've worked it out.
Well, it probably just makes everything extractable, right? I mean, like, you could also just imagine having your U1 emerge from CPI or something, and then there are definitely these charges, right? But I think it's just if you're allowed to use the heavy charges in doing your extraction, then all the entanglement becomes extracted.
That's true. And then, so as I said, if they are heavy, then if you can go up to those energies, you'll be able to extract that much. And otherwise, so you have to be a little careful about whether you're activating the degrees of freedom you've added or not. But I think then it should be possible to map the problem.
Okay, let's think.